In our next section, we're going to learn the fundamental theorem of calculus. And this theorem is basically going to connect the concept of area and those Riemann sums with our antiderivatives, which we learned in section 410. So basically, we are going to learn how to connect derivatives with area. So first of all, this is our fundamental theorem of calculus, what I have written on the screen. It says if we have a continuous function on the interval from a to b, and capital F is an antiderivative of f, then our definite integral, so again, notice that we have those letters, the a and the b, those are my bounds of integration. So this is a definite integral. So the integral from a to b of function f, which we learned was area under the curve, we can find that by finding the antiderivative of f and plugging the upper bound in, then plugging the lower bound in, and subtracting. And so this is going to be a shortcut or a way to avoid using that long Riemann sum process that we learned in the previous section. So as always, I think theorems are easier to understand through examples. So let me just show you what this theorem is telling us by doing an example. So if I want to find the integral from 1 to 6 of 1 over x dx. First of all, this problem is asking me to find the area between the function y equals 1 over x and the x-axis from x equals 1 to x equals 6. To find that area, I can find an antiderivative of 1 over x. And in fact, the antiderivative of 1 over x is natural log absolute value of x. That's just something I have memorized. Normally, when we're finding antiderivatives, we tack on a plus c to indicate that we can add a constant and we still get the same derivative. But with the definite integrals, instead of writing down the plus c, I'm going to write down a line with the numbers 1 and 6 on it. And this is just notation that says I'm going to be plugging the 6 in, then I'm going to plug the 1 in, and then I'm going to subtract them. And so the reason we don't need the plus c is because we are subtracting. So we subtract two antiderivatives, the c's are going to go away. You'll have a plus c and then a minus c. The c's will always disappear. So when you're finding a definite integral, something with numbers or bounds of integration, you don't need the plus c. Instead, we plug in the upper bound, the 6 first. Then we plug in the lower bound, the 1, and then subtract them. Feel free to put this in your calculator. I got 1.79 when I did that. Or you could write the answer as ln 6 because ln 1 is equal to 0. So you're just left with ln 6 or 1.79. And this is the exact area under the curve as well. All right, here's another example. We're going to integrate 5 sine x from pi over 6 to pi over 3. So the first thing we have to do is find the antiderivative. 5 stays there. The antiderivative of sine x is negative cosine x. Again, that's just something I have memorized. So I get negative 5 cosine x. And then again, we don't have to write down the plus c. Instead, we plug in the upper bound, pi over 3. We plug in the lower bound, pi over 6. And then we're going to subtract those two values. All right, let's see. Negative 5 cosine pi over 3. Cosine of pi over 3, that's my 60-degree angle. So that would be 1/2. So -5 times 1/2. And then we've got +5 cosine pi over 6. That's the 30-degree angle. So +5 times 3 pi over 2. And I'm going to just leave my answer as -5 over 2 plus 5 root 3 over 2. All right, here's another one. We're going to integrate from 0 to 1. Square root of x times x plus 2 squared. There is no product rule for antiderivatives. There's no chain rule for antiderivatives either. So what are we going to do? How are we going to be able to find this antiderivative? Well, we're going to have to actually multiply things out. So square root of x is the same thing as x to the 1/2. And then I FOILed out the x plus 2 times x plus 2. That's how I got the x squared plus 4x plus 4. And then I'm going to distribute the x to the 1/2, remembering that when we multiply, we add the exponents. So 1/2 plus 2 is 5/2. And then I got the 4x to the 3/2 because 1/2 plus 1 is 3/2. And then last term, 4x to the 1/2. All right, so again, there's no product rule, quotient rule, or chain rule for antiderivatives. And so that's why I had to multiply everything out. Now I can integrate one term at a time using that power rule where we add to the exponent and divide. So 5/2 plus 1 is 7/2. So I got x to the 7/2 over 7/2. Next term, 3/2 plus 1 is 5/2. So 4x to the 5/2 divided by 5/2. And then finally the last term is 4x to the 3/2 divided by 3/2. Dividing by a fraction is the same thing as multiplying by its reciprocal. So I copy dot flipped. I said dividing by a fraction, I can just flip it and multiply. And then this 8/5 right here, that came from, let's see, if we flip the 2/5, we get 2/5 times 4 over 1. That's how I got the 8/5. And then same concept on the third term. I flipped the 2/3 or the 3/2. It became 2/3. And then when I multiplied straight across, I got 8/3. All right, and then finally we plug in our bounds of integration. So I just made my text a little bit smaller so I have a little more room. It's the same thing I had on the previous screen. I'm going to plug in the 1. I'm going to plug in the 0. And I happen to notice in this case, when you plug in 0, you just get 0. And then I'll subtract those values. So we're left with 2/7 plus 8/5 plus 8/3. I got just a little bigger than 4.5. All right, the next thing I want to explain in this section is something called the mean value theorem for integrals. The mean value theorem for integrals says there exists a number c on the interval from a to b such that when we integrate the function from a to b, it equals f of c times b minus a. Okay, so what is that saying? So basically, the left-hand side of this statement, when you integrate from a to b, the function f of x, that's giving you area under the curve. That's what I've shaded in red on the diagram. So that's what the left-hand side is saying. When we integrate this function, we're finding area under the curve. The mean value theorem is telling me it is possible to create a rectangle with the exact same area. So I can pick some number. There has to be a number, number c, in this interval, somewhere between a and b, such that if I were to draw a horizontal line at that y value, that's my f of c, I would create a rectangle with the exact same area as the shaded region in orange. And in fact, this f of c right here is called the average value of the function. And I have that written down on the next screen. So that's my mean value theorem for integrals. There is some average value of the function such that you could actually draw a rectangle using that y value to give you the exact same area. All right, there we go. Okay, so that f of c is the average value of our function. And in fact, most of the problems we're going to deal with the mean value theorem for integrals is going to actually ask us to find the average value of the function. It's going to ask us to find that f of c. And so just very quickly, if we go back to the previous slide, notice that if I want to solve for f of c, if I want to get the f of c by itself, I have to divide both sides by the b minus a. And that's exactly what I have written down on my next slide. So if we take 1 divided by b minus a times our integral, that is the average value of our function. Another way of thinking about this, when you're finding an average, we know averages, we have to add up a bunch of numbers, and then we divide by the number of numbers. So you can think of the integral, in a sense, is doing the adding part, adding up a bunch of function values, and then we're dividing by the length of the interval to give us an average value. All right, so how does this actually work in a problem? If I want to find the average value of the function x squared minus 6x on the interval from 2 to 5, I can just plug those things into that formula that I just gave you. So we're going to take 1 divided by b minus a. So 1 divided by 5 minus 2, or 1/3, times the integral from 2 to 5 of the function x squared minus 6x. All right, so again, it's a 1/3, and then antiderivative of x squared is x to the third over 3. Antiderivative of 6x would be 6x squared over 2, and we could reduce that to 3x squared. Finally, we have to plug in our bounds of integration. So we're going to plug in the upper bound, 5. Then we'll plug in the lower bound, and then subtract them. So I just put 5 in for the x's. I'll times that by 1/3. Then I put 2 in for the x's. I'll times that by 1/3, and then subtract them. Feel free to put all of this into your calculator if you'd like. I guess I have my steps written out. So I did the inside the parentheses first. And then I did the times 1/3. And then finally the subtraction. And when I was done, I ended up getting -8. So the average value of this function on the interval from 2 to 5 is y equals -8. right, let's do an application problem to illustrate what these definite integrals are telling us now that we can find them with our fundamental theorem of calculus. So this example says a buoy bobs up and down with the following velocity in feet per minute. What is the net displacement of the buoy after 5 minutes? And then part B says, what is the total distance the buoy has traveled during those first 5 minutes? All right, so we're given a velocity function, and we're going to find two different things, and we're going to compare these ideas. We're going to find what's called the net displacement, and I'll explain that in a minute. And then we're going to find the total distance traveled. Okay, and so we have this buoy sitting in the water. It's going up and down according to a sine wave. All right, so let's start with part A. So first of all, when we learned about derivatives, we learned that velocity is the derivative of position. Okay, if you take the derivative of velocity, you get position. And so therefore your position is the antiderivative of velocity. Okay, so if we integrate our velocity, we will get position. If you want to find net displacement, we're just really asking, where is that object? Where is that object located relative to its starting point after 5 minutes? And so if you want to find net displacement, you're just going to integrate your velocity from 0 to 5. And that should tell us where the object is. And again, that's because position is the antiderivative of velocity. All right, so let's actually do that. Let's integrate our velocity. Antiderivative of 2 sine t should be negative 2 cosine t. And then I have to plug in my bounds of integration. In calculus, we are always in radian mode, so make sure your calculator is in radian mode. And then we can plug in the 5, plug in the 0, and subtract those values. It's a negative, so minus a minus became a plus. That's why I have the plus 2 cosine 0. And so I put this into my calculator. Again, I was in radian mode, and I got 1.43 feet. And so what is that telling me? That's telling me the buoy, this object, is 1.43 feet above its starting point. So if it started at what we're calling 0, after 5 minutes, it's about 1.5 feet higher than where it started. Right? So it's giving me the position of the object. Now, it's not this 1.43 is actually not the distance it's traveled. Because this buoy is going up and down, I actually don't know, did it just go up 1.43 feet? Did it go up and then down and then up and then down? Did it cycle through several cycles and that's where it stopped? And so that's what part B is going to tell us, is how far did this object actually travel? All right, so there I have written on the screen. I think I already said this in words, but now we have it written down. So just to kind of summarize, the 1.43 feet is its position or net displacement, where it is located relative to the starting place. Okay, so it is located 1.43 feet relative to starting. But again, I don't actually know how far the object has traveled. It's possible that it went up and then down and ended at 1.43 feet, or maybe it went up and down multiple times and then ended there. And so if I want to find the total distance traveled during the first 5 minutes, I have to really think about what does the graph of this function, this velocity function, even look like. And so I have graphed my velocity function just really lightly. And I graphed this by thinking back to trig class. So I know when we have a sine wave, it goes through the origin, and then it goes up and then down. And then I guess the amplitude would be 2 because of that 2. I didn't really include that on my graph, but those peaks would be at 2. And then the other thing I remember from trig is the period. 1 time around the unit circle is 2 pi. So we should have 1 up and 1 down in 2 pi units. When the velocity is positive, the object is moving up. And that's what's happening in the first half of this graph. When the velocity is negative, when the curve is below the x-axis, the object is moving down. Now, 2 pi is like 6 point something, 6.2-ish. And so we're only interested in what happens from 0 to 5. And so I stopped my shading in. I just estimated, okay, if 2 pi is about 6, maybe 5 is right there. And so from 0 to 5, the object is moving up, and then it starts going down. And so basically, if you want to find the total distance traveled, you're going to have to integrate the positive and the negative regions separately. Okay, total displacement, you just integrate 0 to 5. For total distance, you have to integrate the positive and the negatives separately. If you don't, the positive and the negatives end up, in a sense, canceling each other out. Okay, so where does this graph cross the x-axis? Maybe you just remember from trig, it should cross halfway between. So if the period is pi, it should, or 2 pi, it should cross at pi. Or you could take your velocity function and set it equal to 0. That's what I've done in purple. Divide by 2, so you get sine of t equals 0. And then you have to think about your unit circle. Where is sine equal to 0? That would be at 0, pi, and 2 pi. And so that point I've drawn in purple has to be at pi. It crosses at pi. And so now that we know where it crosses, we can integrate the positive and the negative parts separately. So the positive part, I'm going to set up the integral from 0 to pi, and I'm going to integrate 2 sine t, and that'll tell me how far the object has moved up. And then for the negative region, I'm going to integrate from pi to 5, because we're stopping at 5, and that'll tell me how far the object has gone down. All right, so from 0 to pi, same antiderivative. The antiderivative of 2 sine t is still negative 2 cosine t. Now I'm going to plug in pi, plug in 0, and subtract them, and I ended up getting 4. So this is telling me the object went 4 feet up. And then from pi to 5, same antiderivative. Now I just plug in the 5, plug in the 5, or no, I said that wrong, I think. Plug in the 5, plug in the pi, and then subtract them. Again, make sure your calculator's in radian mode. And I got negative 2.57. So that's telling me the object is then going down 2.57 feet. This matches my answer in part A. We went up 4 feet, Then we went down 2.57 feet. The net result is we are 1.43 feet above our starting position. So what is the total distance traveled? Well, if we went 4 feet up, 2.57 feet down, we have traveled a total of 6.57 feet. Okay, so to summarize in part A, when you're finding the displacement, you don't have to worry about positives and negatives. You just integrate. In part B, when you want to find the total distance traveled, you do have to do the positive and the negative regions separately. All right, last topic in this section. There's lots of theorems in this section, and sometimes this is considered the fundamental theorem of calculus part 2. I actually don't have that theorem written down on the screen yet, but we're leading up to that. Okay, so what I have written down on the screen basically says we can think of the definite integral as a function. And so all I mean by that is we are allowed to put variables into our bounds of integration, and then our answer is going to have a variable in it and end up being a function. Okay, so that's all I mean by this. We are allowed to put variables into our bounds of integration to create a function. So for example, I have this function f of x is defined to be the function or the integral from 0 to x of secant squared t dt. And so we can find this function the same way we would evaluate a definite integral using our fundamental theorem. So even though there's a variable in our upper bound, it doesn't change how we do the problem. What I mean by that is we're going to find the antiderivative. And this is another one I just have memorized. I know that the antiderivative of secant squared of t is tangent of t. And then I'm going to plug in my bounds of integration. So the upper bound is an x. I plug that in for t. I get tan x. The lower bound is 0, tan 0. Tangent of 0 is 0. And so my final answer is tangent x. So this definite integral can be written as the function tangent x. Okay, so we're allowed to have variables in our bounds of integration. Okay, so this is what I was trying to lead up to. This is often called our second part of the fundamental theorem. And this is basically saying, I think I put my bracket in the wrong place. Let me see if I can fix that. But basically this is saying if you take the derivative of an antiderivative, if you take the derivative of an integral, those are inverse operations. So the brackets should be where I drew them in green. If you take the derivative, that's the d dx, of an antiderivative, you should get the original function, right? They're inverse operations, they undo each other. Okay, so let's see how this works by doing an example. I have defined a function to be the integral from 3 to x of t to the 4th dt. I want to find the derivative of this function. So I'm going to do this problem a long way, and then I'm going to show you a short way of doing this. So we can figure out what this function is by finding the antiderivative. If we integrate t to the 4th, we add 1 to the exponent, and we get t to the 5th over 5. I plug in my bounds of integration, and I get x to the 5th over 5 minus 3 to the 5th over 5. So in blue, I have figured out what is this function f of x. And then the problem is asking me to find the derivative. So my function, I've just kind of written it in a slightly different form. X to the 5th over 5 is the same thing as 1/5 x to the 5th. 3 to the 5th is 243, so 243 over 5. So there's my function in blue. Let's see what we get when we take the derivative of this answer. So my derivative would be, let's see, the 1/5 stays there, and then I get a 5x to the 4th. The derivative of a constant is 0. 1/5 5x to the 4th is just x to the 4th. And so the thing to notice here is we took the derivative of an antiderivative and we got what we started with. So notice we started with this t to the 4th, and our answer is x to the 4th. That's not a coincidence, because when you integrate and then take the derivative, you're doing inverse operations. You're undoing those operations. And in fact, if you want to use this theorem, you don't have to show all of that work. You can just right away, without saying any work, doing any work at all, say that, okay, well, the function's variable is x, so when we take the derivative, we will get x to the 4th. All right, let's do a couple more examples with this theorem. So here's another one. Let's find the derivative of the following function. And let's see if we can do this using our shortcut method. And in fact, I haven't even told you how to find the antiderivative of this function, because there's no chain rule for antiderivatives. So we're going to have to use the shortcut. So what is the derivative of this antiderivative? All we have to do is rewrite that function, rewrite the thing inside the integral, but replace the t with an x, and that's it. So again, I took this thing right here, the thing inside the integral, and I put that variable x in for t. And that's my answer. I don't have to show any work. I've just applied my fundamental theorem, part 2. All right, I think I have a couple more examples. So what if your bound of integration is a function of x and not just an x? This is where we're going to have to use the chain rule. And so let me first show you this problem the long way. So I have the function from 0 to sine x of w to the 3rd, and the goal is find the derivative of this antiderivative. So let's do this problem. Oh, I guess I'm going to do it the short way first, and then I'll show you it the long way. Okay. Okay, so the fundamental theorem, part 2, says when you take the derivative of an antiderivative, those are inverse operations, and you will get what you started with. But take this bound of integration and plug it in for the letter. Okay. So that's going to give me sine x to the 3rd. Okay, so again, all I've done right here is I took my bound of integration with the x, plugged it in for the w. Because I put a function inside a function, technically when you're taking the derivative, this is a chain rule problem, and the sine x is your inside function, so you're going to have to multiply by the derivative of sine x, which is cosine x. So if you're plugging something into your variable, which is not just an x, if your bound of integration is more complicated than just an x, you're going to have to multiply by its derivative and that is our chain rule. Now, if you're not convinced, let me show you this the long way and show you that this is indeed the derivative of this antiderivative. Okay, so here's my long way. So I actually took the time to integrate w to the third. Okay, so I looked at the w to the third. What is the antiderivative? I get w to the fourth over 4. I plugged in my bounds of integration. So I got sine x to the fourth over 4. And then when you plug in 0, 0 to the fourth over 4 is just 0. Okay, so the function that we're working with, function f of x, is right here, sine x to the fourth over 4. So to take the derivative, I have to use the chain rule. I bring down the 4, sine x to the third, and then this divide by 4 is a constant, it stays there. And then I have to multiply by the derivative of the inside, which is cosine x. These 4's cancel out, and you are left with the exact same answer I got in purple. We'll do another one like this. But the idea is, when you're finding the derivative of an antiderivative, inverse operations, they go away. And so what you have to do is you take your bound of integration that has a variable in it, you plug it in, so that's the first part, and then make sure you multiply by the derivative of that bound. That is your inside function. All right, so here's one more. Find the derivative of the following function. This one's a tiny bit different. Notice that the bound of integration that has a variable in it is the lower bound. There's a constant in the upper bound. How does that impact our answer? Well, we always subtract the lower bound, so that just means our answer is going to be negative. All right, there's my answer. How did I get that? Again, the idea is the 6 is a constant, so when you take its derivative, you get 0. And then the variable is in the lower bound, so that's why we have the minus. Let me clear that. So I took my lower bound, the e to the x, I plugged it in for w, and that's this first part right here, e to the x to the third. Then I had to use the chain rule, and I had to multiply by the derivative of the inside function. The inside function is that e to the x. The derivative of e to the x is e to the x. All right, so again, to summarize, it's a negative because the variable is in the lower bound. That will always happen. If the variable is in your upper bound, your answer is going to be positive. The second e to the x was the chain rule. That was the derivative of my inside function. Finally, we could simplify this answer a little bit. The part with the parentheses, e to the x to the third, this part right here, you can multiply the exponents and you get e to the 3x. And then e to the 3x times e to the 1x, when we multiply, we add the exponents. And so that's how I got a final answer of negative e to the 4x. So 3x plus 1x gave me 4x. I know there's a lot of theorems, a lot of content in this section. Really, I think two main ideas here. Main idea one was we can find definite integrals by finding the antiderivative, plugging the bounds of integration in, and subtracting. And then main idea number 2, when you take the derivative of an antiderivative, those are inverse operations. They undo each other. So that is it for this section. As always, let me know if you have any questions.